Hey, good morning, everyone. Um, so first few logistics announcements. So about the lecture. So today the lecture will take place. It's going to be a 45-minute lecture. And afterwards, Lídia will also upload the next lecture, which would be like this 2-hour lecture, which she was supposed to give on Tuesday, but instead that will be the lecture that will come after today's. Okay, also another logistics announcement is that next week, instead of my tutorial, we're gonna have an external person from a quantum computing company who will give like a tutorial on the basics of quantum computing and programming a quantum computer. So that's gonna be quite exciting. So I recommend you all to come. Okay, great. Then let's start with our tutorial for today. So again, sorry that I've uploaded the exercise sheet only yesterday evening. Yeah, that's a bit of a delay on my side, but it's fine. We're gonna look at the exercises now. So in this exercise sheet, we'll look at the thermal states and the properties of the thermal states. There's going to be a more thorough introduction about the thermal states in the lecture, but let me just, I'll just briefly also motivate them here. And the properties that we'll look at will be the composability of thermal states and also how the thermal states can be derived from just some energy related assumptions. But let's start with thermal states. Okay, so let us look at the following Hamiltonian. So H, which would be just sum from 1 to D, EI, II. So to which physical situation does this Hamiltonian correspond to? So as we've seen in the last exercise sheet with this system and the battery, we can actually portray the physical situation here as some in a way that the system in consideration has these D energy levels. This is how energy goes. And suppose that this is the level number I, this is I minus 1, this is I minus 2, this is I plus 1, and so on. And each level has the energy of the corresponding eigenvalue. So this level has EI plus 1, this level has energy EI, EI minus 1, EI minus 2, and so on. And now let us abstract a bit let us go away from the quantum situation. And let us imagine that we're just in a classical situation where we have lots of these energy levels. And for example, we're looking at the classical situation over gas in some confined space. And we know that the particles of gas, they can occupy one of these levels. So each particle has a particular energy. So maybe, as you already know from thermodynamics, or if not, this is also quite intuitive, something that in this case defines the energy of the particle is its temperature. So as in usually when we consider like gas, classical gas in thermodynamics, we say that the kinetic energy of the gas, which is which is proportional to the square of the speed of the particles, is essentially the average of these value for all particles is defined by temperature. So the average energy of the gas particle is proportional to the temperature. And in that way, it can be seen that it is the temperature that kind of that defines how fast the particles are in the gas. But it also, but suppose that we have then this gas with a temperature T, and then we are looking at how the particles would occupy these different energy levels that we are given. And of course, then it becomes obvious that the higher the energy is, kind of the less particles will be able to kind of reach this energy, because it's only the average energy that is proportional to T. And suppose if we are looking at the energy level, the energy of which is kind of bigger than the temperature, then the number of particles on that level would be less than the number of particles at the level with the energy which corresponds to the temperature T. So essentially, like in what we would have in the gas, we would have a certain distribution over particles for different energy levels. And the characteristic way this particles would behave, like this distribution would behave, is that kind of the population, which is essentially the number of particles that that end up at the particular energy level, this population reduces as the energy of the level goes up. So, and so as E increases. And in classical situation, this distribution is described by so-called Boltzmann distribution. So Boltzmann distribution at temperature T just tells us that the probability of finding the particle, the gas particle, for example, at the level EI, at the level of energy EI, is the following. EI e to the power minus beta EI over Z, where beta is just 1 over kBT, so T is the temperature, and kB, I think my screen froze, sorry. Let me stop sharing for a moment. And share again. Now should be fine. So where beta is just 1 over kBT, where T is the temperature we're considering, and kB is just this Boltzmann constant, which we don't need to concern ourselves with because we're not gonna like calculate anything. But just for you to know, it's approximately 1.38 by 10 to the power minus 23 joule by Kelvin, joule over Kelvin. And Z is called partition function, and it just essentially ensures that the probability distribution is normalized. So this is partition function. Now let us go to the quantum scenario. So imagine that, so we looked at this classical scenario with these Gauss particles just occupying different energy levels according to this Boltzmann distribution. Now let us go to the quantum case where we just have a quantum system which has these this number of degrees of freedom with different energies. And we know the probability with which every level is occupied. Hence, we can write, and this is a classical probability distribution, and we know exactly how to express it in terms of when we're looking at the quantum system. We express it in terms of density matrix. So we can write essentially the quantum state of the system as the density matrix, which is dictated by this Boltzmann probability distribution. So I'm going to be PI, and we can rewrite it. So it would take a more compact form. So instead of PI, we just insert e to the power minus beta EI over Z. We have here. Okay, and what we can notice is actually that the expression in the nominator is actually exactly can be written just in the matrix form as the exponential of the matrix minus beta h, where h was the Hamiltonian that we were considering. Why? Because the Hamiltonian is diagonal in the energy basis, and so if we just insert our diagonal Hamiltonian into the exponential, the action of the exponential would be that it would be just this all diagonal terms are going to get exponentiated. And then that's going to be it over Z. And since Z is just the normalization constant, so that, for example, in this case, we need the trace of the density matrix to be 1, which corresponds to the idea that we need to kind of the probability distribution to sum up to 1. Then the partition function Z, we can actually also write it as just trace of the matrix in the denominator. And in this case, the trace of the density matrix will be exactly 1. And so this state is called Gibb state, or thermal state. And it describes the state of a quantum system at thermal equilibrium. So the idea is that we have this system which we put in some kind of reservoir at temperature T, and then we wait for some time until the kind of the equilibrium is reached, and then after that the state of the system would be described by this density matrix. Of course, given that the system is described by the Hamiltonian that we've written earlier. Okay, so now let us see what are the properties of such states. So the first property we will take a look at is decomposability. Suppose that we have two systems, which are described by Hilbert spaces HA and HB, and these two systems are also described by a joint Hamiltonian. And the joint Hamiltonian, in this case, we assume that it can be written as just the as a sum of individual Hamiltonians on the systems A and B. So we're looking at the Hamiltonian, which is non-interacting. So just Hamiltonian on system A plus identity on system B plus identity on A, Hamiltonian on B. So this is non-interacting. There is no term which would allow to couple systems A and B. So we're looking at these two systems, and suppose that they're both at temperature T. Then let us, in this case, look at the joint thermal state at temperature T. Of systems A and B. So yeah, usually also we label these thermal states as just tau of T. And remember that the dependence on T is hidden in the variable beta, because beta is proportional to 1 over T. But usually people do things with beta because it's a bit easier than always writing 1 over KT and so on. So I'll just operate with beta, but keep in mind that beta is 1 over T. Okay, so let me write this thermal state, tau of AB at the temperature T. So per definition, this would be e to the power minus beta HAB over Z, which is just the trace of e to the power minus beta HAB. Let us look now at the matrix e to the power minus beta HAB. If we insert our definition of the Hamiltonian HAB, then we arrive to exponential of minus beta HA identity B minus beta identity A HB. It's prettier. What is this? What we can see immediately is that since there is no interaction term between systems A and B, we can simultaneously diagonalize or find a basis where for the joint space of systems A and B, such that the Hamiltonians HA and HB would be both diagonal in that basis. So essentially what we do, we just take the system A and diagonalize the Hamiltonian HA, then we take system B and diagonalize the Hamiltonian HB. And together these two bases in which these Hamiltonians are diagonal give us the basis for the joint system AB. So hence, we arrive to, so this is the way we diagonalize HA. Then This is the way we diagonalize HB. And here now what we notice is actually that both of these terms in the argument of the exponential are actually both diagonal. So what we have here is that we have the exponential of the diagonal matrices, or like we have the exponential of a sum of two diagonal matrices, which means that in this case, we are actually allowed to express this exponential as just the product of the exponential of the first term by the exponential of the second term. Where rect is exponential of minus beta. I write back the HA since we already know that the way we expressed it was diagonal. Beta. Yeah, so this is maybe just as a comment, I'll do it here. So this is crucial to remember that it's not always that you can conclude from seeing, oh, I have exponential of some matrix A plus matrix B, or I can just do the same I do with in the case of real numbers and say, oh, this is just equal to exponential of A by exponential of B. So for the matrices, this is not always true. However, it is true if these two matrices are simultaneously diagonalizable. So if there is a certain basis in which both terms in the argument are diagonal, then you can kind of do this intuitive thing that we usually do in in calculus, right? And in this case, this is exactly what happens because both terms are explicitly diagonal. Okay, and now it's rather easy. So what we get here is maybe we just write it as a sum here. So sum over n minus beta to the power n factorial HA 1b to the power n. Here we have sum over m minus beta to the power n factorial identity on A, HB to the power m. And this one leaves us with HA to the power n by the identity on B. This leaves us with identity on A, HB to the power m. And hence, what we end up with is just sum over n m minus beta to the power n factorial HA to the power n tensor product sum over m minus beta to the power m over m factorial HB to the power m, which is actually just exactly this matrix exponentials e to the power minus beta HA tensor product e to the power minus beta HB. So hence our conclusion is that tau AB of t is just e to the power minus HA tensor product e to the power minus beta HB over, so what we had was ZAB, but ZAB is just a trace of e to the power minus beta H. So what we get here is just a trace of the expression in the nominator, which is, because it's a tensor product, it's just a product of traces. tensor product with this expression here. Okay, and what are these two expressions? These are exactly the thermal states per definition of the systems A and B. Okay, so what kind of conclusion that we reached? If we have a composite system at the thermal equilibrium at temperature T, and the subsystems of the system that do not interact, then the thermal state of the joint system can be written as just a tensor product of the thermal states of the subsystems. Okay, hence we can just generalize this for n systems. So if we have a Hamiltonian H acting on n systems such that they do not interact, so it's just sum of their individual Hamiltonians. Let's say H1, identity on the rest of the systems plus identity on the first system, Hamiltonian of the second system, identity on the rest, and so on. Then the thermal state tau of T for such a system can be similarly expressed as just the tensor product of thermal states on each of the individual systems. And this makes, and physically how to understand this. So if we have n systems which do not interact, then and the joint system is a thermal equilibrium, then it makes sense that every part of the system also has to be in thermal equilibrium. And this is exactly the statement of composability. Okay, so this was the first property that we looked at. Then the second property has to do with how does the thermal state arise to be. And this is a bit of a thorny way, but let's see how we can get there. And this is the way we're looking at what energy is and what temperature is. So to start, let us just first consider a qubit. The same one as we considered in the previous exercise class, with a Hamiltonian H epsilon 1, 1. So again, the physical picture that you should have in mind is that the qubit has 2 degrees of freedom. First we label 0, second we label 1, which in this case can be represented as 2 energy levels with the energy difference epsilon. Okay, so the first question is, if we given this Hamiltonian of this qubit, what is the thermal state of the qubit? And first, a bit of intuition. So you get how physically this is again represented. So we have 2 levels. One level is energetically higher than the other one. We also have a given temperature, right? Which kind of corresponds to how, like in a sense, how high on average the particles can go, or in this case, the degree of freedom of the qubit. So what we would expect in the end that the distribution gives us, especially given Boltzmann distribution, is that, of course, that the population of the energy level corresponding to the state 1 is exponentially lower than the population of the level corresponding to 0. So in the density matrix, the term in 0, 0 has to be exponentially bigger than the term corresponding to 1, 1. So these two diagonal terms. And let us confirm our intuition. So we have tau of t, which is again per definition e to the power minus beta h over trace e to the power minus beta h. So here we have as e to the power minus beta epsilon 1, 1 trace of the same thing. Let us write this in the matrix form. So what we have up would be e to the power minus 0, 0, 0 minus beta epsilon. And here we have the trace of the same thing. And e to the power of this matrix is just the matrix 2 by 2. And diagonal terms are exponentiated. So e to the power 0, e to the power minus beta epsilon. And the trace would be e to the power 0 plus e to the power minus beta epsilon. Okay, so what we arrive to is 1 over 1 plus e to the power minus beta epsilon, 0, 0. Here we have e to the power minus beta epsilon, 1 plus e to the power minus beta epsilon. And here exactly we see what we've expected, because the diagonal term corresponding to 0, 0 is exponentially higher than the diagonal term corresponding to 1, 1. So all good. Then let us calculate the average energy for this thermal state. So the average energy is just tau, trace of tau of t, h. So this is just an easy exercise, trace of this matrix multiplied by h, which is just this matrix. And if you calculate this, what you get is epsilon e to the power minus beta epsilon over 1 plus e to the power minus beta epsilon equals epsilon over 1 plus e to the power beta epsilon. And if we include temperature instead of beta, then we would have epsilon over 1 plus e to the power epsilon over kt. One can look at the different kind of borderline cases to see if our derivation is correct, just as a sanity check. So for example, if we look at the case when the difference between two levels in the qubit is much smaller than the temperature, which means that epsilon is much smaller than kt, then essentially what we get is that this term tends to 0 in that limit, and then the average energy would be just epsilon, because the denominator would be 1. Which makes sense, because if the temperature is much higher than the difference between two levels, then essentially we would have no problem of bringing the state from state 0 to state 1. On the other kind of side of this limiting cases is the case when the temperature is much smaller than the energy gap between level 0 and 1. in that case, it would be close to impossible to intuitively close to impossible to kind of bring the state of the system from being at 0 to 1 just by having this temperature, which corresponds to the fact that in this case, the exponential of so e to the power epsilon over kt would be close to infinity, would be going to infinity in the limit where epsilon is much bigger than kt, and hence the average energy would be tending to 0. So it would be almost impossible to bring the state up to the state 1. And so this is just a sanity check of why our energy derivation, like our final kind of equation for the energy, should be correct. It's just sometimes good, like if you get some kind of equation in the end, it's sometimes good to do a sanity check and look at some limiting cases where one variable is much bigger or much smaller than the other. Then usually physically, intuitively, you can tell what's gonna happen, and then the formula also has to mimic that behavior. Okay, so we looked at 1 qubit. Now let us look at n qubits. And we assume that, again, these are just n identical qubits from the previous point, which are non-interacting. So their Hamiltonian is essentially just sum over their individual Hamiltonians, also with the identity on the wrist. So again, the systems don't interact. Okay, so and suppose now, for the first, just to start, suppose that the system, this joint system of n qubits, is in the thermal state. So that the joint state is thermal. Then from composability, that we just derived before, we can already conclude that since this is a non-interacting Hamiltonian and the joint state of the system is thermal, then it can just be expressed as a tensor product of thermal states on individual systems. So tau of t is tau1 of t, so on, tensor product tau n of t. And in this case, when we want to compute the global energy, which is, of course, we can compute as trace of h tau of t. Since h is non-interacting and tau of t is just separable into a tensor product of the individual states, thermal states on the subsystems on each of these qubits, then actually we can take a leap here. Of course, you can write out h and tau kind of formally and then prove it by just writing it out. But also we can already see here that this the average global energy would be just a sum of the individual average energies on each of these n-qubit systems. And so it would be just n by the energy E that we've computed in the previous part, which was N by epsilon over 1 plus e to the power epsilon over kt. So we just insert it here, multiplied by N. And this is what we get. So this is the global energy of global thermal state. Okay, now let us make the following assumption. So we've computed this global energy from the assumption that the global joint state is thermal. So suppose that now we don't want to. So now we just have this. But perhaps we don't want to assume that the joint state is thermal. We want to kind of come to that for some other considerations. But for just to start, let us now suppose that all we know is that the total energy in global can be written as some np epsilon for the system of the n qubits, with p some number from 0 to 1, such that np is a natural number. So essentially, what this means is that the global energy is some integer number by the energy epsilon, which kind of characterizes the energy gap of a single qubit. And so this is the first assumption that we make. So we forgot about how we just computed the global energy for the thermal state. We just assume that we have this energy of the global state. And the first thing that we would like to compute is, if we're just given this energy and we're not given any notion of temperature, then actually we can derive what temperature is if the average energy, if the average global energy is such, and also if we additionally assume that the state is still thermal, the joint state is still thermal. So if the joint state is still thermal, then we can find the temperature just from knowing the average global energy. Why? Because we know that the global energy for the thermal state is n epsilon over 1 plus e to the power epsilon over kt. And what you need to do here is just equate it to np epsilon. And then you can express t as t a function of n, this p. Let's say just p because n is kind of fixed. So it's going to be some natural logarithm. I'll let you do it yourselves. Yes, and in this case, another thing that we just want to write out here, just to compare, to have something to compare to later, is that if we look at the reduced state of the first qubit out of this n qubits, it's just a thermal state, right? Because we know that the thermal state, if the joint system is in thermal state, then each of the subsystems is also in thermal state. And then the reduced state is just the state of that system because the joint state is separable. So then the reduced state is just the state that we already written earlier. Okay, now let us go to the way we can drop the thermal state assumption. So now suppose that we still have our convention about the global energy, that it is an integer number multiplied by epsilon. But now suppose that we don't want to assume that the global state is thermal. We don't want to assume. It's just some state. And what we would like to assume for simplicity is that, suppose that we know that the state is P1, so it's some state psi, and it is diagonal in the energy basis. So which means diagonal, I mean that if we write the density matrix, which corresponds to the state, then this density matrix will be diagonal in energy basis. Which means, in other words, if we write it mathematically, means that the Hamiltonian commutes with the density matrix corresponding to that state. Also, just to remind you, if two operators commute, this means that they have a joint basis in which they're both simultaneously diagonal. Okay. So we have a state psi on which we have two conditions: that it is diagonal in energy basis, and the energy of the state, which is just the trace of psi h, which is the global energy, is this P and epsilon. So the set of such states for the given global energy is called an energy shell. So we denote the set of the states as omega, global, and we define it as all states psi, such that they're diagonal in an energy basis, and the energy is equal to the global energy which we were given in the beginning. Okay, now the question is, what is before we proceed further and see how it helps us to identify this set, is that we want to see what is the structure of this set. Oh, there was a question. There was a question in the chat. What is the energy basis? So the energy by the energy basis, I mean the basis in which the Hamiltonian is diagonal. So the Hamiltonian, we can write it out as just, when we can write out the Hamiltonian as just a sum over I, EI, II. So just as a matrix for which the only the diagonal terms will survive, which would correspond to the energies of the corresponding level, then this is what we call an energy basis. Does this answer the question? Yeah, good. Okay, so let us first understand what is the structure of such states. So we have the global Hamiltonian is kind of only the sum, essentially the sum of the local Hamiltonians, right, on the qubits. And the local Hamiltonian of one qubit is just is essentially diagonal in the 0-1 basis of a qubit. This actually means that the way we wrote our global Hamiltonian is already kind of its diagonal form. Because if you look back at our joint Hamiltonian of n qubits here, which is this one, then essentially every term in the sum is diagonal because it is a tensor product of diagonal matrices. Then we already have that our Hamiltonian is initially diagonal. And then the basis that this Hamiltonian is diagonal in is actually just kind of the tensor product of all bases, of all 0-1 bases of the individual qubits, right? Since every local Hamiltonian is diagonal exactly in this 0-1 basis of the individual qubit. Which means that the states of this basis consist of zeros and ones on the corresponding qubits. So essentially, it would be, for example, n zeros, n times 1, 0, and all zeros. So 1 and n minus 1 zeros, and so on. So kind of all of these possible combinations of 0 and 1s. In total, of course, this gives you 2 to the power n combinations or states in the basis. Then what we want are essentially the state, since we know that the states that we're looking for, the state psi and this energy shell, they have to be pure. So first they have to be diagonal in the basis of energy basis, which means that they actually have to be a state from that basis of the energy basis. So they have to be one of these states with zeros and ones. We just don't know how many zeros it has to have and how many ones. But this is quite easy to establish. So the energy of the state which has, for example, m ones and n minus m zeros, which corresponds to the fact that the state corresponds to the system having m qubits in the state 1 and n minus m qubits in the state 0. And we know that since the Hamiltonian, the physical system of the qubit corresponds to the level 0 to the state 0 having energy 0 and a state 1 having energy epsilon, then if we have a state which has m qubits in a state 1 and n minus m qubits in a state 0, the energy of such a state, the global energy would be just m epsilon, because it's only the qubits in the state 1 that will actually give you the contribution towards global energy. Since we know that the global energy has to be NP epsilon, then we can say that M equals NP. So omega global as a set contains states psi such that NP qubits are in the state 1 and N minus NP, which is just N by 1 minus P qubits, are in the state 0. Which means that actually we can, using the kind of some combinatorial permutations, we can say that these states psi I, which belong to this omega global, are the states psi I, which is some permutation which we label as sigma I of the qubits in the state 1 tensor product NP times 0 tensor product N1 minus P times. So essentially all the states that belong to this energy shell are just correspond to this to the permutations of the state of the qubits for the state where you have NP qubits in the state 1 and N1 minus P qubits in the state 0. So these are all possible qubit permutations. And how many are such states? As many as there are permutations. So then the power of the set omega global, which is just a number of its elements, is just a number of ways we can choose NP positions out of N positions, which is just choosing NP from N. I'll use, I don't know which notation you're more familiar with, so I'll write both. So either you write it as this NP, N, NP in brackets, or I am more used to the notation C, choose NP from N. But in any way, this is just N factorial over NP factorial, N minus NP factorial. So this is the number of states that we're considering. How does this help us? So actually, we can use this to describe our ignorance. If we start with the assumption that we don't know what state we're looking at, we just know kind of the average global energy, which is NP epsilon. And we also have some information about the state, namely that it's pure, it is like, it is diagonal on an energy basis, and that's it. Then how do we describe the global state? Well, in this case, we can describe our knowledge about the global state as just a uniform distribution over all elements of the set omega global. Because even though we have this only limited information about about what governs the state, we actually were able to identify all possible states, namely the set of the states that the system can take in this case. And hence we can describe kind of our knowledge about the states as just a uniform distribution over all the states in this set omega global. And this would actually give us the density matrix description of the system. So we can describe our knowledge of the global state, our knowledge, or rather our ignorance in a way, because we still assume that this distribution is uniform. Over all elements of omega global. Then we can write that rho global equals, here we insert the normalization, which is just the power of the set, sum over all psi I and omega global psi I. Okay, so it's a bit difficult to analyze this state, like as we have like all psi i's, all this possible permutations. What we can do is we can look at the reduced state of the first qubit. And as a spoiler, and also something that you'll probably have to finish on your own, is that if we look at the case where we have a lot of qubits, where n is much bigger than 1, essentially you'll need to look at the limit of n goes to infinity. In this case, you will find that the reduced state of the first qubit, if the joint system is in this rho global state, will actually asymptotically be a thermal state, which kind of conveys the intuition that, write it here, spoiler, thermal state. So it conveys the intuition that all the information we had about the state was that the global energy, the average global energy, has to be this NP epsilon. Then we put some additional restrictions, which are actually much stronger that they have to be if we're doing this, if we want a general result. But in any way, there were some additional restrictions on that it has to be pure and so on. And in that case, actually, because we don't have any further information about the system, are like, because, and also because the density matrix describes our knowledge, or in this case, lack of knowledge about the system, what we would arrive to would be actually the thermal state, because because this is kind of the free state, because this is it would correctly correspond to the amount of the ignorance that we have about the system, because we wouldn't actually know anything. I don't know if this makes a lot of sense, but I hope it does. And so let me maybe just pave a way to kind of show this. So row 1, the reduced state of the first qubit, is we need to trace all the systems from 2 to n from the global state. For this, let us first look at the state psi I that we have in the sum. How can we rewrite the state psi I? So we know that psi I is just this permutation of all possible states which have np1s and n1 minus p0s. Okay, so the idea here is that kind of separate this the set of states of psi I into the states which kind of start with 1. Sorry, which kind of start with the state 0 on the system 1, tensor product the rest. Something on all the systems. And kind of the states in the set which start with 1 on system 1, and then there is something on all the other systems. So what is the remaining state of this on the systems from 2 to n? So the remaining state of the systems from 2 to n, what we would have is we took 1, 0, which means that we're left with np1s still, and n1 minus p minus 1 zeros. And here we took 1, 1. So we're left with np minus 1 ones and n1 minus p zeros. All right, so we can actually rewrite how the states look like. So for the subset of the states which start with 0 on system 1, we can write them as 0 on system 1, tensor product all possible permutations on the state which has np1s and n1 minus p minus 1 zeros. This is this one. And here it's kind of the same, so we can write it out as 1 on the system 1 and all possible permutations on the state which has np minus 1 once and n1 minus p zeros. Okay, then we can separate our sum in row global as following. So these normalization states. So first we sum over states which start with 0 for system 1, which leaves us with like sum over I 0, 0 on system 1 by permutation number I. I don't think it was a smart idea to start writing in the bottom of the page, so I'll go to the next one. So row global normalization, then we start sum over permutations 0, 0 system 1 tensor product permutation number I on the state with NP1s and N1 minus P minus 1 zeros. And also permutation on the same but conjugate state. And also now, because it's ones and zeros, I like to mix them so much. Yeah, this is just essentially the complex conjugate. Plus the same thing for 1, 1. So this is just summing over the states which start with 1 for system 1. And here we have NP minus 1 ones and N1 minus P zeros, and also by complex conjugates because it's a density matrix. Okay, now we can try to take the trace. Okay, so when we take the trace, we need to kind of, in this case, sum up over the basis for the systems. Sum up like for all the states of the basis for the systems from 2 to n, which is essentially this. Also, their basis is just this, all the possible states with all possible combinations of 0 and 1s, except for the fact that now the total number of 0 and 1s has to be n minus 1 because we're tracing out n minus 1 system. And the only non-zero kind of contributions which would be given to this partial trace, he writes this. Now we're writing row 1, right, which is the trace to n from row global. So yeah, so the only non-zero contributions will be coming from states which are like other permutations of this type of state or the permutations of this type of state. And we know the exact number of the states that would give a non-zero contribution to trace. So for the state 0 of the matrix row 1, it will be exactly the number of states which have NP1s and N1 minus P minus 1 zeros, which is the number of ways you can choose NP positions from N minus 1 position. And I don't need the tensor product here anymore. Plus, for 1, 1, it would be a number of ways you can choose NP minus 1 positions because you have like NP minus 1 ones from N minus 1 position. And of course, there is also this global normalization, which is just the number of ways you can choose NP from N. Okay, so we found the reduced matrix of the first qubit. Now what I leave for you to do at home is take the limit of n going to infinity, so the limit of many qubits, and see that this state actually would coincide with the thermal state, or essentially find what is the asymptotic of the reduced state of the first qubit in this case. And it would be a thermal state for the temperature, yeah, that we found earlier. Okay, so this was a bit of a combinatoric mishap. I guess maybe you need a bit more time to wrap your head around this, because in the end it's just yeah, games with 0 and 1s in states, in the basis states. Yeah, and today in the lecture you'll hear a bit more about thermal states and the motivation behind thermal states. Yeah, I think this is all for today. Are there any immediate questions? Oh, can I give a solution to sheet 10, exercise C? If only I remembered. Let me see. Oh, did you mean the exercise 3? Do you mean this exercise? Oh, 1C. What was it? It's about POVM elements. Oh, sorry, I didn't write it in the solution. Okay, I'll include it in the solution. Sorry about this. I'll just re-upload the solution. Okay, let me mark this. I kind of forgot that I had that question there. Okay, any other immediate questions? Great, then thanks for attending. Yeah, if you have any questions, send them by email. Have a good rest of the day. See you next week.